So in this course, we're going to see what is time series data, what is the tick stack, what is InfluxDB and how it correlates it to the tick stack, what are InfluxDB use cases. We're going to install it locally using Docker. We're going to install InfluxDB remote in the cloud. We're going to have a look at some sample data. We're going to import that data and we're going to run our first query. That's all in the introduction. In the InfluxDB basics, we're going to talk about key concepts and how to design a schema. In the query language section, we're going to look at what is InfluxDB, the select, the where, group by, into, subqueries, and joins. In the advanced section, we're going to look at the storage engine, writing and reading data with the HTTP API. We're going to look at authentication and authorization. We're going to look at retention policies and continuous queries. In the last section, we're going to look at the InfluxDB integrations. We're going to install Chronograph and play with it. And we're going to see how to use InfluxDB plus Grafana. So it's a lot to take in. So this will give you a good introduction into InfluxDB, and you'll be ready to use it in production right away after you completed this course. Nowadays, and especially in the future, all our devices generate some sort of timestamp data. Think of smartphones with all their sensors, activity trackers like Fitbit, machine monitoring, application monitoring, and especially Internet of Things. This kind of data is super valuable information, especially in business, predicting machine failures, anomaly detection, recommendations based on previous collected data, and so on. The growth of these time-based data creates a need for time series databases. Traditional relational database management systems like Oracle, SQL Server, or MySQL are less built for this kind of data, and eventually you wish you have chosen InfluxDB. Time series databases are often compared to other databases. There are multiple types of databases that get built up for comparison. Mostly, these are distributed databases like Cassandra, MongoDB, or HBase. When comparing time series databases with Cassandra, MongoDB, or HBase, there are some remarkable differences. First, those databases require significant investment in developer time and code to create the functionality provided out of the box with time series databases like InfluxDB. Specifically, developers will need to write code to shard the data, aggregate it, downsample functions, data eviction, and lifecycle management. You may wonder, isn't it possible to do this with an existing database like MySQL? A workable implementation of a time series database can be deployed in any conventional SQL-based relational database, provided that the database supports both binary large objects, better known as blobs, and user-defined functions. SQL statements that operate on one or more time series quantities on the same row of a table or join can easily be written as the user-defined time series function operates comfortably inside of a select statement. However, time series functionality, such as a sum, operating in the context of a group by clause, cannot be easily achieved. Possibilities for native time series databases are limited, but InfluxDB from InfluxData is one of the best in its area, especially with the whole tick stack ecosystem. InfluxDB is able to handle high write and read requests. It's written in Go and it compiles into a single binary. Go was a language created by Google. InfluxDB is fairly a new product, but it's very mature and it's part of InfluxData's tick stack. The installation is super simple, as I will show you in this course. InfluxDB does not depend on any other services like Redis, HBase, HDFS, and so on, in comparison to classic big data systems like Hadoop. These big data systems are composed out of a lot of components, and this makes them hard to maintain, upgrade. Your ops team is gonna love it, and is gonna be happy to maintain this. Now we have a better understanding about time series databases. I first want to discuss time series. What is time series data actually? A time series is a series of data points indexed in a time order. Most common, a time series is a sequence taken at the same interval. Examples of time series are CPU monitoring, Apple stock data, number of connections per second, the temperature reading taken at your house at hourly intervals, and so on. Time series are very frequently plotted via line charts, and in one of our labs I will show you how to do this in Chronograph and Grafana. Time series are used in statistical, signal processing, pattern recognition, finance, weather forecasting, and so on. Largely in any domain of applied science, engineering, and applications and survey metrics, which involves measurements at a certain time interval. Time series data is a collection of data points within a certain time. All data points are variable measurements within a certain time interval. Interval between data points should be the same. This even saves disk, but I will gonna explain this later on. Time between one measurement and the next should be the same, but doesn't necessarily mean it is the same. Each data point only has one measurement, and this is important, but I will explain it to you later on. Regular time series versus irregular time series. Regular time series, the orange data points, are measurement points happening at the same interval, like DevOps monitoring like CPU, RAM, stock data, and so on. Irregular time series are measurement points happening at random moments in time. User clicks, orders in a restaurant, website visitors, and so on. You may have heard about the tick stack or me mentioning it in a previous lecture. Tick stack is composed out of Telegraph, InfluxDB, Chronograph, and Capacitator. Telegraph. Telegraph is a plugin-driven server agent for collecting and reporting metrics. Telegraph has plugins or integrations to source a variety of metrics directly from the system it's running on, pull metrics from third-party APIs, or even listen for metrics via TSDB or Kafka consumer services. Telegraph is a metric collection daemon that can collect metrics from a wide variety of inputs and write them into a wide area of outputs. It's plugin driven for both collecting and outputting of data, so it's easily extendable. It's written in Go, which means that it's compiled into a standalone binary that can be executed on any system with no need for external dependencies. No npm, pip, gem, or other package management tools are required. With over 100 plugins already written and available, it's easy to start collecting metrics from your endpoints. Some examples of these plugins are Docker plugin, Apache, Kafka, Kubernetes, PHP, Redis, and so on. You can even use Telegraph to parse the input data formats into metrics. The Telegraph architecture supports your workflows and does not force you to change your workflows to work with the technology, whether you need to push or pull metrics, or you need to fit it with your current architecture instead of the other way around. Telegraph's flexibility makes it an easy decision to implement. InfluxDB. This is the main focus of the course, and I will get into this in the next lecture. Chronograph. Chronograph is the administrative user interface and visualization engine of the platform. It makes the monitoring and alerting for your infrastructure easy to set up and to maintain. Chronograph offers a complete dashboarding solutions for visualization of your data and monitoring your infrastructure. Example dashboards are provided that allow you to get started very quickly. You can also create customized dashboards to meet your needs. Chronograph is also the visual administrative tool for your Influx data deployments and supports the administration of open source instances of Influx data as well as Influx enterprise instances. Chronograph also provides user management and user authentication services. Chronograph is the user interface used for Capacitator. Capacitator. Capacitator is a native data processing engine. It can process both streams and batch data from InfluxDB. It lets you plug in your own custom logic or user-defined functions to process alerts with dynamic thresholds, match patterns from metrics, compute statistical anomalies, and perform specific actions based on these alerts, like dynamic reload balancing, Capacitator integrates with HipChat, Opsgenie, Alerta, Sensu, PagerDuty, Slack, and more. Today's modern applications require more than just dashboarding and operator alerts. They need the ability to trigger actions. Capacitator's alerting systems allow you to do this. Alerts are published to a topic, and handlers subscribe to a topic. This pops-up model and the ability for these to call user-defined functions make Capacitator very flexible to act as the control plane in your environment. It can perform tasks like autoscaling, stock reordering, and Internet of Things device control. Capacitator is designed to process streaming data in real time. It can be deployed across the infrastructure as both a pre-processor downsampling and performing advanced analytics before shipping the data to InfluxDB, and a post-processor allowing all the higher precision data to be stored in Hadoop, for example, for further analysis. Capacitator is very easy to use, but it's also very powerful. Capacitator provides a simple plugin architecture or interface that allows it to integrate with any anomaly detection engine. Capacitator can integrate with machine learning libraries, pattern matching engines, rules engines. This makes Capacitator a powerful control system calling user-defined functions that automate the complete system. Now we're going to talk about the main focus of this course, InfluxDB. InfluxDB is the time series database in the TIC stack. InfluxDB is used as a data store for any use case involving large or small amount of timestamp data. It's written in Go and has no external dependencies. That means once you install it, there is nothing else to manage, such as Redis, Zookeeper, Cassandra, HBase. InfluxDB was built from the ground up to be a modern time series database and to handle high write and query loads. This was built in from the beginning. InfluxDB is targeted at use cases for DevOps, metrics, sensor data, and real-time analytics. Some extraordinary features are like automatically expiring and deleting any unwanted data from the system. InfluxDB can handle millions of data points per second. Working with that much data over a long period of time can create storage concerns. A natural solution is to downsample the data, keeping the high precision raw data for only a limited time, and storing the lower precision resolution, summarized data for much longer or even forever. InfluxDB offers two features: continuous queries, CQ, and retention policies, RP, that help you automate the process of downsampling data and expiring old data. InfluxDB also offers a SQL-like query language for querying the data. It allows for high throughput ingest, compression, and real-time querying of the same data. In one of our labs, you will see this impressive ingest throughput when we start importing data or run queries on them. It has been created to feel familiar to those coming from other SQL or SQL-like environments, while also providing features specific to storing and analyzing time series data. InfluxQL also supports regular expressions, arithmetic expressions, and time series specific functions to speed up data processing. InfluxDB provides a high performance write and query HTTP or HTTPS API. Some use cases are custom DevOps, real-time analytics, Internet of Things and sensor data, equities trading, monitoring, GPS services, automation, points of sale system, and many more. Here are some use cases from InfluxDB. They're used by tech giants as well. eBay uses InfluxDB across a variety of projects, including monitoring cloud infrastructure services, like Elasticsearch as a service, performing anomaly detection on IT infrastructure, and providing data quality dashboards. Nordstrom uses Influx data to support their company-wide cloud infrastructure monitoring and control needs. They use Influx data to monitoring Nordstrom.com to ensure customers have a great online shopping experience. Bbox uses Influx data as the Internet of Things data platform to continuously monitor their geographically dispersed 85,000 solar units. They use this data to provide predictive maintenance and are becoming a data-driven organization. IBM needs to maintain high availability across their entire system in order to fulfill the promise of delivering full protection against online fraud. The team uses DevOps monitoring techniques driven by InfluxData, InfluxDB, and Telegraph. Specifically, they use Telegraph to collect operational metrics, store them in InfluxDB, and present the metrics and events data to the operations department using a Grafana dashboard. The data collected is infrastructure and application performance data that allows Cloud Operations Department to monitor and maintain the whole system, which contains hundreds of virtual servers. There are many more use cases like that, and I suggest you check out the testimonial page on influxdata.com/customers/testimonials. Alright, now the fun part can begin. Now we got a firm base, we can go ahead with the installation of InfluxDB. In this lecture, I'll be explaining how to prepare our exercise environment locally for Windows and for Mac, as well on how to install this on the cloud. Don't worry if you never worked with Docker before, I'll guide you through it. Hi there and welcome back. Right now we're going to install Docker for Mac. I'm going to show it to you how to do it in Windows as well, but this is the Mac lecture first. So we're going to go to docker.com, get Docker Mac, we'll download it, get Docker, and as you can see it's downloading right now. Download has completed, I'm going to open it. It opened, and the installation is quite simple, just drag and drop, and it's installed. Start Docker, open. As you can see above here, the Docker icon is going to pop up. You can see Docker is starting. So this is basically how to install Docker. So right now we're going to install Docker for Windows. We're going to docker.com. Go to Get Docker, Windows. Download from Docker Store. Get Docker CE for Windows, the stable one. Download is happening right now. Gonna open the download. The flashing on the screen was that I had to give permissions for the installation to run. It's unpacking the files, and the installation succeeded. So that was basically how to install Docker for Windows. In this lecture I'll be showing you how to install InfluxDB on the cloud. First of all, I advise you to create an account at DigitalOcean, log in to the machine, and then I'm going to show you how to install InfluxDB. Alright, now our droplet has been initialized. We log on to the droplet and we're going to install InfluxDB. First of all, we're going to grab the Debian package. So that's downloaded, and we're going to install it. See how fast it went? That's because InfluxDB doesn't have any external dependencies, it's written in Go. Now we're going to test it, Influx. Now you see it's not running yet. I'm going to do systemctl. Alright. And it started. Now I'm gonna do show databases to see what's in here. And there's nothing in here yet. So if you prefer to do the exercises here, also fine. I'm going to be using throughout the course mainly Docker, but it's up to you. It basically comes down to the same thing. Now we're going to take a look at the sample data. During the summer, I went on holiday to France with my kids, and I collected some data from my iPhone. You can see my speed and the altitude I was driving on. We're going to use this sample data throughout the course. Alright, now we're going to check if everything is installed correctly. We're going to do this by running docker ps. This shows if Docker is running and if there are already containers running. Like you can see here, there's no container running. We're going to start by creating an empty configuration file for InfluxDB. It's pulling the latest InfluxDB container. This can take a while, especially if it's the first time you've done it. Now we're going to start by building the container. This actually executes the Docker file in the directory. Then we're going to start a container running InfluxDB. When we run docker ps again, you're going to see the container is running. It's created 5 seconds ago and it's up and running 4 seconds ago. These are the local ports being forwarded to the container. So right now we can run the most exciting part, the client, to interact with InfluxDB. Couldn't do this by running this. See, now we have a shell. We can do show database. See, no database are in there at the moment. Right now we're going to start by importing some data. I'm going to do this. See how fast it processed, like 1,178 inserts. It took like only a second or so. When we execute the show databases again, you see, he created the database Holiday France. Alright, so we're going to start a client container again, because it's time for our first query. Very important phase in this course. So we're going to see what's in here. Show databases. I'm going to use Holiday France. I'm going to do a simple select query. Select star from speed underscore milliseconds. Hooray, we did our first query. It's a very simple one, but we'll get into the more advanced later on. Alright, let's talk about the InfluxDB key concepts. In InfluxDB, these are the most important key concepts. A database, a field key, a field set, or a field value, a point, tag key, tag set, or a tag value. We got series, we got timestamp, we got a measurement, and we got a retention policy. Now I'm going to explain each bullet point to you. A database. An InfluxDB database is similar to traditional relational databases and serves as a logical container for users, retention policies, continuous queries, and of course your time series data. Fields. Fields are a required piece of Influx data structure. You cannot have data in InfluxDB without fields. It's also important to note that fields are not indexed. Queries that use field values as filters must scan all values that match the other conditions. As a result, those queries are not performant relative to queries on tags. More on tags in one of the next slides. In general, fields should not contain commonly queried metadata. A point. A point is the field set in the same series with the same timestamp. Tags. Tags. Tags are a very important piece of InfluxDB, and if you do this right, your queries will be lightning fast. In this example, you see location, Biron, France, Paris, a car, Audi, BMW. Tags. A tag value is extra metadata. Examples: Biron, France, Paris, BMW, and Audi. A tag key is also extra metadata, like location or car. A tag set is a tag key plus tag value. A tag set is also all the different combinations of tag key value pairs, like location Paris, car Audi, location Biron, France, car BMW. This is very important for the cardinality of your data structure. Series. A series is a collection of data that share a retention policy, measurement, and tag set. A timestamp. Since InfluxDB is a time series data store, every measurement does have a timestamp. A timestamp is expressed in epoch time. Epoch time is the number of seconds or milliseconds, depending on the resolution of your data, that has passed since the 1st of January 1970. A measurement. The measurement acts as a container for tags, fields, and the time column. The measurement name is a description of the data that are stored in the associated fields. Measurement names are strings, and for any SQL user out there, a measurement is conceptually similar to a table. Retention policies. A retention policy describes how long InfluxDB keeps the data, duration, and how many copies of the data that are stored in the cluster, replication. I'm going to talk about the schema design. Before we get started, it's important to remember, and I can't stress this enough, tags are indexed, fields are not. So that's important to keep in mind throughout this course. So alrighty, schema design. We're going to start by explaining about what not to do. There are many different use cases, so we're going to talk about some of the things that are super bad to do in InfluxDB, and you surely will regret later on. Unlike a graphic-style measurement storage system, in InfluxDB it's not a good idea to encode data into the measurement name. As you can see, speed milliseconds.yorn.biron.france speed equals, that's really a bad idea. A good example is below. It's split up into tags. These things are better put in as fields and tags if you store it in the measurement name. It's going to significantly restrict your ability to query the data later on. So here we see some examples of graphic-like. These things are better put in fields and tags. If you store it in the measurement name, it's going to significantly restrict your ability to query that data later on. So here we see some examples of graphic-like data, also known as DevOps data. Speed milliseconds.yorn.biron.france speed equals 13.75, and then the timestamp. Another example is another graphic-like example of CPU data. Now the good part. In InfluxDB, the way we should prefer to encode that information is to use the speed or CPU as a measurement, and the other metadata we would like to be storing as tags. That means that we can use it in group by clauses, we can use it more readably in the where class. We won't have to use regular expressions in our own where class, which definitely slows things down if you can use equality operators or negation operators as opposed to regular expressions. The query is much faster, and in fact it would also be possible to store all of these together. We could store multiple fields in the field set. However, the graphic protocol is well established in the world, so it's possible to use a plugin to translate that data correctly into InfluxDB line protocol data. But you might think, I can change the way we set metrics to InfluxDB. The graphic protocol is well established in the world, so I chose that when I designed my app. No worries, it's possible to use a plugin to translate this data into correct InfluxDB line protocol data. It takes the input as described here and uses a template to translate it into InfluxDB line protocol. In this example, you see some graphic-like example. It takes the input and translates it into the correct line protocol data. Don't overload tags with metadata. So what's another bad practice is to overload tags. So here we see an example where cpu.server equals server-1337.eu-west.amazon value 23 and a timestamp. That's two different pieces of information that we could have encoded into a single tag. Server is the tag key, I would say, but we have two pieces of metadata here. We have both the server name, it's server1337, located in the EU West, and the provider is Amazon. It's way better to separate those out into two different tags, where host equals server1337, region equals EU West, and provider equals Amazon. We're being more specific so the tags are more descriptive of their properties, and again, can't stress this enough, we're avoiding having to do something like regular expressions to match against host in any region or match against EU West with any host name, which would be inevitably if we were using a single tag. We'd need to use regular expressions to separate that out, and again, regular expressions are not as performant, so you really should avoid using them in our queries. Queries will become more performant, more readable, more repeatable, and easier to use with graphing tools like Chronograph or Graphite. So conclusion, remember to keep your metadata into separate tags. If possible, don't use tags that have a high variability due to RAM restrictions and limitations. Other best practices. Functions only accept fields. Regular expressions only work on tags, and I don't recommend you using them. Group by only works on tags. Other best practices. Don't use the same name for a field and a tag. Use enough tags, but be careful with using too many tags. Get the precision correct. Milliseconds can mean that your data was in 1970, or in seconds, it can mean it is in 2185, and that's in the future, so that's impossible. When using milliseconds, there is way more traffic. It's larger on disk, and write throughput can get saturated. Functions only accept fields. If you do a select count, for example, this will always need a field and not a tag. Anything in group by needs to be a tag. If you pass anything to a function, it's a field. Losing info can be to the wrong data type. 10 measurements in a database is okay. 1,000 measurements in a database, it's not okay. Now we understand the key concepts. I'm going to move on to the data model. Tags. As this graph shows, car speeds map to a measurement. For MySQL users, a measurement is like a table. In the legend, here is an example of how a tag is being used. A tag is the legend that contains the metadata of what the measurement represents. Like this, driver equals Joran, me. Tags are indexed and thus faster to query on than fields. A collection of tags. A collection of all tags is a tag set, like driver Joran, location Biro. A set are all valuable combinations of key value pairs. The y-axis. The values on the y-axis are actually called fields and are also a key value pair. The key is speed, the value is 14.3. The possible values of fields are floats, integers, strings, and booleans. A collection of fields is called a field set. For example, speed equals 14.3, altitude equals 123. X-axis. The x-axis is a timestamp. It represents as a number in Unix epoch time. Epoch time is a time that has passed since the 1st of January 1970 after midnight. All data has a time component, as this is a time series database. InfluxDB uses something called a line protocol. This is how measurements are coming into the database. You see speed, meters per second, is a measurement. The location is a tag set. In this example, the location is only one tag, thus it's also the tag set. Speed is a field value. Description is a field value. Speed plus description is a field set. And at the end, there's a timestamp in milliseconds. Alright, and now the most important part of this course, InfluxQL. In this section, I'm going to be covering InfluxQL. It's InfluxDB SQL-like query language for interacting with the data in InfluxDB. I'm going to talk about the schema exploration and data exploration. These are the major keywords in InfluxQL. As you can see, they're pretty advanced. You get some schema exploration queries here. And they always start with show. Show databases, show series, show measurements. Now we're going to talk about the select statement. This is used for the data exploitation. You can see select field key, tag key from a measurement name, or multiple measurement names. Here you see an example of a select query. First we start the Docker container using the command described above. Then we do show databases. You see which databases are there. In this case, our holiday friends. We're going to use holiday friends. And then we're going to do a simple select query like we did in the beginning of this course. Select star from altitude, limit 2. The limit 2 is to limit the amount of records that are returned. In this case 2. If you have a dataset of a couple million records and you do a select star, it's going to take a while to run, and it's unnecessary. That's why we limit it always. It's always a good practice to test queries with a limit. Right, we're going to test these queries. First we're going to do a Docker run to start the Influx client. I'm going to do a show databases. So you got holiday friends in there. You do want to do use holiday friends. Now he's using that database. I'm going to do a simple select query. Select start from altitude m limit 2 records. Alright, got some records back. I'm going to do the same for the other measurement. Select start from speed underscore milliseconds limit 2. Now we got the results back from the other one. I suggest you try this yourself so you get acquainted with the syntax. Now we'll be using select to select specific tags and fields from a single measurement. In the examples below you see select time, semicolon altitude, from altitude underscore m limit 2. You'll see it will return the 2 records. I'm going to do the same, select time, speed, from speed underscore milliseconds, limit 2. As you can see, it gives the same result. Alright, now we're going to select some specific tags and fields from a single measurement. I'm going to do select time, and altitude, from altitude underscore m, limit 2. Alright, we got the result back, and as you can see we only got time and altitude returning because we passed them through the select statement. I'm going to do the same thing for speed millisecond. Select time, speed, from speed underscore milliseconds, limit 2. As you can see, we got the same result, time and speed. Select specific tags and fields from a single measurement and provide their identifier type. We're still using the database holiday friends. I'm going to do select description field, location tag, altitude field, from altitude underscore m limit 3. As you can see, he will return the 3 records. Alright, now we're going to select the specific tags and fields from a single measurement and provide their identifier type. I'm going to do select description, which is a field. I'm going to location, which is a tag. Altitude, which is also a field, from altitude underscore m, limit 3. Select all fields from a single measurement. Select star. Field from altitude underscore m, limit 3. As you can see, it will return the 3 records. Alright, now we're going to select all the fields from altitude underscore m and limit them by the same amount. Now we returned only the field types, so the tag types are left out. Select a specific field from a measurement and perform basic arithmetics on it. In this case, select altitude divided by 1000 to get the altitude in kilometers from altitude m, limit 3. As you can see, he will divide the actual altitude by 1000. Alright, now we're going to do a query with some basic computations on it. We're going to do select, open brackets, altitude divided by 1000 to get it in kilometers from altitude underscore m. I'm going to limit it again by the same amount. In the data, the altitude was stored in meters. It was 193 meters. So if you divide it by 1000, we get it in kilometers. This one is a very handy feature in InfluxDB that you can do such a simple computation on the data. Select star from altitude m, speed, milliseconds, limit 3. This is going to be used to select all data for more than one measurement. Okay, now we're going to do a simple query to select all data from more than one measurement. I'm going to do select star from altitude underscore m, speed underscore milliseconds, and limit it again by the same amount. As you can see, it returns every record, but it's limited by 3 from altitude m and from speed milliseconds. Data exploitation. Where. Here you see an example of how to use a where clause. Select all data that have specific field key values. So we're going to select everything bigger than 194 and limited by 3. As you see, you will get all the records with a value of altitude higher than 194. Alright, let's try to get all the results with the altitude higher than 194 meters. I'm going to do a select star from altitude underscore m, where altitude higher than 194, limit 3. As you can see, we got all the results back with an altitude higher than 194. Select data that has a specific string field key value. So we're going to do a select star from speed underscore milliseconds, where speed description equals speed in meter per second, limit by 3. As you can see, you will get the 3 results back, where the description is speed in meter per second. Alright, let's get back all the results where the description is speed in meter per second. Select star from speed underscore milliseconds, where speed description equals speed in meter per second, limited by 3. Here you see we get the results back where the speed description is speed in meter per second. Select data that has a specific field key value and perform basic arithmetics on it. Select star from speed milliseconds, where the speed plus 1 is higher than 12 and limited by 3. As you can see, you will get all the records back that are higher than 12. In below example, you also see select star from speed milliseconds, where speed plus 1 is smaller than 12, limited by 3, and you get all the records back, which are the speed plus 1, but still smaller than 12. Okay, let's try to get all the results back with the speed value plus 1, but bigger than 12. I'm going to do a select star from speed milliseconds, where speed plus 1 bigger than 12 and limit by 3. Boom, we got everything that's the speed plus 1 and bigger than 12. Gonna do the same thing, but then everything smaller than 12. Gonna select star from speed underscore milliseconds, where speed plus 1 is smaller than 12, limit by 3. As you can see, you get all the values back, where the speed plus 1 smaller than 12. Select data that have specific field key values and tag key values. Select star from speed millisecond, where location equals Biron, France, limit 3. As you can see, you will get all the results back, where the location equals Biron, France. Alright, we're gonna do a simple select, where a specific field key value equals Biron, France. Select star from speed underscore milliseconds, where location equals Biron, France. Oh, this is a string, Biron, France. Because it's the actual value, it's coded differently. Limit 3. Boom. As you can see, you got 3 results back with where the location is Biron, France. Select data that has a specific tag key value. Select star from speed milliseconds, where location equals Biron, France, and the speed plus 1 is smaller than 12, or the speed plus 1 is bigger than 13. As you can see in the values getting returned, you'll see some values being bigger than 13 and some values smaller than 10. Alright, let's see if we get all the speed where the speed value plus 1 is smaller than 12, or the speed value plus 12 is bigger than 13. So we're gonna do select star from speed milliseconds, where location equals viral friends and speed plus 1 is smaller than 12, or speed plus 1 is bigger than 13. I'm gonna limit it this time by 10 to get a decent amount of returns back. And we made a typo here. I forgot a quote. Bam. You can see all the results. Everything is smaller than the speed plus 1, 13, and or everything is bigger. Now we're gonna do some select data with specific timestamps. We're gonna do select star from speed milliseconds, where time is bigger than now, minus 150 days. But we don't get any results back. Why is that? That's because we imported the data with the wrong precision. It's very important that you run into it during a course instead of in real life, because when you import it and you give it the wrong precision, it's gonna think it's 1970 or 2185. That's the difference between seconds and milliseconds, which I mentioned in the previous lecture. Now we're gonna rerun the import with the correct precision with the above command. We're gonna do a docker run. As you see, I added a precision as parameter to the command. Now we're gonna do a simple select star from speed milliseconds, where time is greater than 30th of June 2017, limited by 3, and you'll see you getting results back. I'm gonna see if I'm still in the right directory. Alright, we see the sample data course. I'm gonna copy the command here. And it's gonna import the data again, but using the precision S. Boom. He processed 1178 inserts. Pretty fast, right? Not even a second. Now I'm gonna start a Docker container again using the client. Now I'm gonna do show databases. Database is still there. Use holiday friends. Okay. Now we're gonna see if it worked. I'm gonna do a select star from speed underscore milliseconds, where time is bigger than 2017, June 30th, time 21, 24, 0 seconds, C. That's just the time protocol. Limit 3. Boom, and we got the time back. Yay, we imported it with the correct data. Select data that has specific timestamps. Because we have a new data set now, we can do a select star from speed milliseconds, where time now minus 100 days, limited by 3. Keep in mind that you may have to increase these 100 days depending on when you're taking this course. Alright, now we're gonna select star from speed milliseconds, where time is more than now and 100 days. So it's between now and 100 days. And for this lecture, I'm not gonna limit it by 3. I'm just gonna run it as is. I don't have that many data points. It's just to give you a test how long it takes to get a couple of hundred records returned. As you see, it takes no time at all. It's a lot of records, but nevertheless, it's super fast. Group by. Another very important thing is a group by. For this, we're going to import a bigger data sample set. We're going to use the sample data course 2 file. I'm going to import it. As you can see, when you do show databases, you see we got a new database. NOAA water database. We're going to use that database and we're going to try our select queries on it. Alright, let's start with importing the data. Don't forget the precision flag in seconds, else the data will be in 1970. I'm going to use the sample data course2 file. I'm going to import it. It's a much bigger data set, so it's going to take a little longer, but a little longer, I mean milliseconds, as you can see here. Okay, we're going to start an Influx client container again. Boom, we're connected. I'm going to do show databases. And you see you got a new database here. We're going to use that one. And then we're going to do a simple select query on it, like select star from H2O underscore feed limit it by 3 because it's a bigger data set, and we got some results back. So our data is imported and is working correctly. We're going to do a select mean water level from H2O feed group by location. As you will see, you will get the average height of the water depending on the location, Coyote Creek or Santa Monica. Alright, so let's get the average water level grouped by every location. So we're going to do select mean water level from H2O underscore feed. I'm gonna group by location. Best to quote it, just best practice. Location. Here you go. Now you got the mean of the water level in Coyote Creek and Santa Monica. These are the two values where you grouped them on location. These two are tags, as you can see here. Select mean index from H2O quality, group by star, limit 2. As you see, you get all the results back, but it's grouped by every other tag. So you get the location back, Coyote Creek, but you get it back 2 times because it has a different RAN tag. The above one is RAN tag 1 and below one is RAN tag 2. That's what the group by star does. Okay, now we're going to query the mean index from H2O quality and group by star. This means he's actually going to do a combination of all the tags, thus a tag set. I'm going to do select mean index from H2O underscore quality, group by star to get the tag set, limit by 2 to not get too many combinations. As you can see, he grouped by Coyote Creek and Coyote Creek, but because it has a different RAN tag, as you can see it has value 2, this value 3, he split up the 2 because it's grouped by on star, thus the tag set is different here. It's not only limited on location, but also takes into account the RAN tag. It does the same thing for Santa Monica, and you can see RAN tag 1, RAN tag 2, RAN tag 3. This is especially useful if you have, let's say, multiple sensors in the same location, but like a meter apart from each other or something like that, and you have multiple tags. Group query results into 12-minute intervals. Select count water level from H2O feed where location is Coyote Creek and the time is between 2015 end time is between also 2015, group by time 12 minutes. As you see, he will count the amount of measurements taken in that time frame. Alright, this is useful if you got a lot of sensor data and you want to know how much data is actually being recorded in, let's say, a 12-minute interval. I'm gonna do a select count water level from H2O_feet where location equals Coyote Creek, and time is more or equal to 2015 August 18th 000000 C, and time is smaller or equal to 2015 August 18 time 30 C group by, and now the magic comes into play, time 12 minutes. You can see you recorded at this timestamp 2 measurements, 2 measurements, and 2 measurements. So this is super useful in InfluxDB that you can do stuff like this. So let's talk about the into. The into clause writes query results to a user-specified measurement. The into clause supports several formats for specifying a measurement. Into writes data to the specified measurement. If you're using the CLI, InfluxDB writes the data to the measurement in the use database and the default retention policy. If you're using the HTTP API, InfluxDB writes the data to the measurement in the database specified in the DB query string parameter and the default retention policy. Into database name, retention policy name, measurement name, writes data to a fully qualified measurement. Fully qualify a measurement by specifying its database and retention policy. Directly renaming a database in InfluxDB is not possible, so a common use for the into clause is to move data from one database to another. The query above writes all the data in the speed underscore meters per second to the copy speed underscore milliseconds database. The group by star clause preserves tags in the source database as tags in the destination database. The following query does not maintain the series context for tags. Tags will be stored as fields in the destination database. Alright, first we're going to start by selecting the database. Use holiday France. We're going to do select star into copy underscore speed underscore meters per second from speed underscore milliseconds group by star. As you can see, he has written 1170 measurements, and this is the epoch time 0 I was talking about, the timestamp that doesn't make any sense when doing operations like this. When moving large amounts of data, we recommend sequentially running into queries for different measurements and using time boundaries in the where clause. This prevents your system from running out of memory. The code block below provides simple syntax for those queries. You can see them here, the rename in smaller pieces when dataset is huge. You see the where time is now minus 100 weeks and time now min 90 weeks grew by star. In the next query we're gonna have a different boundary, and that's how we rename the database in smaller pieces so you don't run out of memory. You can write the results of a query to a measurement. The query writes its result, a new measurement, copy underscore speed. If you're using the CLI, InfluxDB writes the data to the use database and the default retention policy. If you're using the HTTP API, InfluxDB writes the data to the database and the retention policy specified in the DB and retention policy query string parameters. If you do not set the retention policy query string parameter, the HTTP API automatically writes the data to the database default retention policy. The response shows the number of points, 7605, that InfluxDB writes to copy underscore speed. The timestamp in the response is meaningless. InfluxDB uses epoch 0. That's the timestamp in 1970, in the 1st of January, as a null timestamp equivalent. Alright, let's write the results of a query to a measurement. I'm going to do a select speed into copy underscore speed from speed underscore milliseconds or meter per seconds, where location equals bureau France. I'm gonna run it. Boom. You see the epoch 0 timestamp, and he has written 1170 records or measurements. Now we're gonna do show measurements. And you see he created the into copy speed. We got the copy speed here. Let's do a select star from copy speed. And you see he created a measurement with only the speed, no location or whatever tag, only this values with the correct timestamp. This query writes the result of a query to a fully qualified measurement. Fully qualify a measurement by specifying its database and retention policy. The query writes its result to a new measurement, speed underscore milliseconds. InfluxDB writes the data to the copy underscore speed underscore milliseconds database and to the auto-generated retention policy. Note that both copy underscore speed and underscore milliseconds and out-again must exist prior to running the into query. We'll get into retention policies later. The response shows the number of points, 1170, that InfluxDB writes to speed underscore milliseconds. The timestamp in the response is also meaningless. Another common use case of the into query is downsampling. This query aggregates data using the InfluxQL function and grew by time clause. It also writes its result to the speed underscore milliseconds underscore downsample measurement. The response shows the number of points, 3 in this case, that InfluxDB writes to speed underscore milliseconds underscore downsample. The query is an example of downsampling, taking higher precision data, aggregating those data to a lower precision, and storing the lower precision data in the database. Downsampling is, like I said, a common use case for the into clause. Okay, let's talk about InfluxQL subqueries. InfluxDB performs the subquery first and the main query second. The main query surrounds the subquery and requires at least the select clause from the from clause. The subquery appears in the main query's from clause and it requires surrounding parentheses. InfluxQL supports multiple nested subqueries per main query. This query returns the sum of the maximum speed values across every tag value of location. InfluxDB first performs the subquery. It calculates the maximum value for speed underscore millisecond for each tag value of the location. In this example, you can see how we're going to calculate the mean difference between two fields. We're going to do a select mean difference which is the outcome of the subquery, from select cats minus dogs as the difference, from pet care. First it's gonna do the select cats minus dogs as difference from pet daycare, and then you're gonna perform the mean on it. You can also calculate several mean values and place a condition on those mean values. The query returns mean values of the water level field that are greater than 5. InfluxDB first performs the subquery. The subquery calculates the mean value of the water level from 2015, 08, 18 AM through 2015, 08, 18 and 30 minutes past 12 hours, and groups the results into 12 minutes intervals. It also names the output column all_the_means. Next, InfluxDB performs the main query and returns only those mean values that are greater than 5. Notice that the main query specifies all_the_means as the field key in the select clause. This query returns the sum of the derivative of average water level values for each tag value of location. InfluxDB first performed the subquery. The subquery calculates the derivative of average water level values taken at 12-minute intervals. It performed that calculation for each tag value of location and names the output column water_level_derivative. Next, InfluxDB performs the main query and calculates the sum of the water_level_derivative values for each tag value of location. Notice that the main query specifies water_level_derivative, not water_level or derivative, as the field key in the sum function. Let's talk about joins. I think this will be my shortest lecture in this course, but joins don't exist in InfluxDB. There are some major disparities between SQL databases and InfluxDB. SQL joins aren't available for InfluxDB measurements. Your schema design should reflect that difference. And as we mentioned above, a measurement is like a SQL table where the primary index is always preset to time. InfluxDB timestamps must be in Unix epoch, GMT, or formatted as a datetime string valid under RFC 3339. The InfluxDB storage engine. In-memory index. The in-memory index is a shared index across shards that provides the quick access to measurement tags and series. The index is used by the engine, but it's not specific to the storage engine itself. WAL. The WAL is a write-optimized storage format that allows for writes to be durable, but not easily queryable. Its writes to the WAL are appended to segments of fixed size. Cache. The cache is an in-memory representation of the data stored in the WAL. It's queried at runtime and merged with data stored in the TSM files. TSM files. TSM files store compressed series data in a columnar format. File store. The file store mediates access to all TSM files on disk. It ensures that TSM files are installed atomically when existing ones are replaced, as well as removing TSM files that are no longer being used. Compactor. The compactor is responsible for converting less optimized cache and TSM data into more read-optimized formats. It does this by compressing series, removing deleted data, optimizing indices, and combining smaller files into larger ones. Compactation planner. The compactation planner determines which TSM files are ready for a compactation and ensure that multiple concurrent compactations do not interfere with each other. Compression. Compression is handled by various encoders and decoders for specific data types. Some encoders are familiar, static, and always encode the same type the same way. Others switch their compression strategy based on the shape of the data. Writers and readers. Each file type, if it's a wall segment or TSM files or tombstones or whatever, has writers and readers for working with the formats. The HTTP API is a mean for querying data in InfluxDB. In our previous exercises, we used the Influx CLI quite extensively. To perform a query, send a GET request to the /query endpoint, set the URL parameter DB as the target database, and set the URL parameter Q as your query. You may also use a POST request by sending the same parameters either as a URL parameter or as a part of the body with application/x-www-form-URL encoded. We're going to be seeing some examples in this lecture of how to use the HTTP API to query and to write data to the database. We're going to create a database using the CLI. You're going to do a curl-i-xpost, all caps, HTTP to the local host on the InfluxDB port /query. Going to use --data -URL encode, double quote Q equals create database mydb. This is going to create a database in InfluxDB called mydb. Okay, let's try this example. I'm going to do a curl-i-xpost HTTP /localhost port 8086 /query -data -URL encode equals Q equals create database mydb. See, we got the response back 200 that it was okay, and the result here. So we created the database. Now we're going to write a single point to the database. We're going to do a curl-i-xpost to the local host with the endpoint write. Then we're going to pass the parameter mydb. I'm going to say data is binary, and then I'm going to add a point to that database. To add multiple databases, you can see the example below. When writing points to a file, it's basically the same thing, except we're going to use the @ and then the name of the text file. This is going to upload all the data that is in the text file and put it in the database. Alright, so we just created the database. Now we're going to write a single data point to it. Okay, now we're going to write a single point to the database. We're going to do a curl-i-xpost to the local host, to mydb we just created, and then we're going to add some data to it. Boom. We got a 204 back, which is good, which means he accepted it, so the data is now in InfluxDB. Okay, now we're going to add multiple points at once to the database. It's basically the same thing, only just providing more data points. Gonna do it like this, enter. You can see you got a 204 back, which means InfluxDB accepted the request, so the data is now in InfluxDB. To read the data from the database using the HTTP API, we're gonna do the following. We're gonna send the query to the /query endpoint. We're gonna select the database, and we're gonna provide it a query. In this case, select value from CPU_load_short, where region is US West. Now we're gonna retrieve the data we inserted in the previous lab. So we're gonna do this. It's curl-g from localhost, where InfluxDB is running on, query pretty true, so it's gonna return it pretty. It's gonna query from mydb. And it's going to do a select value from CPU load short, where region is US West. Boom. So here you see the pretty result back, and we got some data points here. We got this one, and this one. These are the ones we just inserted. You can also perform multiple queries. I'm going to do a curl-g, and we're going to send that query to /query endpoint of the local host with the InfluxDB port. We're going to specify which DB to use, and then we're going to provide the queries separated by a semicolon. So basically this query is the same as the previous one, but only it's separated here with the separation key. It's going to use the select value from CPU load short, where region is US West, and select the count from the CPU load short, where region is US West. So it's basically doing two queries. You can see the result we got back from our previous query, it's the same. And this is the result of the query we added. So it does two queries at the same time actually and returns you the result. This is very useful. You can also see the timestamp again of a count is epoch 0, while the data of the imported values is this value. Chunking. Chunking can be used to return results in stream batches rather than as a single response by setting the query string parameter chunk equals true. Responses will be chunked by series or by every 10,000 points, whichever occurs first. To change the maximum chunk size to a different value, set the query string parameter chunk size to a different value. For example, get your results in batches of 500 points with this query. You can see we're going to pass the query select start from speed underscore milliseconds, and we're going to add a chunk size of 500. Now he's going to return the data in batches of 500 measurements. HTTP API responses. When you get a 200 back, in most cases that's okay, unless you screwed up the query and it doesn't actually has to return any data. When you get a 400, there's something that InfluxDB couldn't understand in the request. So you basically screwed up and you should check your query. When you get a 500, the system is overloaded or significantly impaired. So operation screwed up or something is wrong with your setup and you have to investigate on the system level. Okay, now we're going to talk about authentication and authorization. Authentication and authorization is very important. I don't have to explain that, I hope, but by default in InfluxDB, authentication is disabled. So all users have all privileges, and if you would pass credentials to InfluxDB, they're silently ignored if authentication is disabled. Authorization is only enforced once you have enabled authentication, which makes sense, but nevertheless it's good to mention. It's very similar to SQL user authentication and authorization. It's as well for the CLI as well as the HTTP API. There are three ways to do this on the HTTP API. We're going to see that later on. It's authenticate with the basic authentication and authenticate by providing or query parameters or via the body. What is the difference actually between authentication and authorization? Authentication, simply put, is who can come in. Authorization is who can access what once they're in. When setting up authentication and authorization, sometimes you run into issues. So here's a short list of the important error codes to remember. You got a HTTP 401 unauthorized. That means no authentication credentials or incorrect credentials. That means a request by an unauthorized user. Now we got some general user management examples. So you can set a password if you want to change the password for a user or want to change it for the monitoring application or whatever. It's easy to drop users. To remove them, just simply drop user yarn and the user is deleted. Then we got InfluxDB authentication. So we're going to create a user yarn with password, the strong password with all privileges. If you execute that and you do show users, you will see user yarn admin is true. After we've done that, you have to enable the authentication by setting the auth enable to true in the HTTP section of the configuration file. So you're going to do a VI or Nano or whatever text editor you're accustomed with, and you're going to go to etc influxdb, influxdb.conf, and then you search in the HTTP section for auth-enable equals false, and you set that to true, you save it, and you restart InfluxDB for the settings to take effect. Once the authentication is enabled, you can connect to Influx using a username and a password, like this in this example, but there are a couple of other ways to do this as well. You can use environment variables, so you don't want your password to be like typed in on command line all the time. You can put it in the environment variables of certain users or certain applications. Simply export influx_username, all caps, with the name of the user, export influx_password with the password, and then you can do a simple echo of these variables with a $sign in front of them, just to see what's in there, just to make sure you didn't make a typo or whatever more. And then when you simply type influx on the command line, it will authenticate and log you in automatically. Another way of doing that is just typing influx without the environment parameters being set, and then type auth. Then InfluxDB will prompt you with a username and password. Once you enabled authentication, you also have to authenticate through the HTTP API if you do request through that. It's simple, basic authentication. It's just a curl-g on the URL and port /query -u, and then the username colon, and then the password. And then all the rest is pretty basic, like we've seen in previous chapters. You can also authenticate by providing query parameters. This is quite simple as well. You do a curl-g, you do the query, !u is the username, and p equals the password, and then the same is like in the previous example, and then it will authenticate and run that query for you. Another way of doing this is authenticate by using the request body. This means the format is a little bit different, but it drills down to the same thing. It depends on what application you're using or how you want to implement it. Authorization. So in the previous slides, we discussed how you can create users and how you can let them in with the username and password. Now we're going to see how we can restrict access to certain users to certain databases. So authorization is only enforced once you have enabled authentication. By default, the authentication is disabled. All credentials are silently ignored if authentication is disabled, which makes sense. And all users have all privileges if authentication is disabled. This is super important, especially when you install InfluxDB on a cloud environment. When people do a simple port scan and they find out that your database is open, they can delete data, add data, and whatever more. You don't want that. So please, if you're installing this for the first time on DigitalOcean or whatever more, or you're using a public IP, please fix this first before continuing. So the user types and privileges. You got admin users, which have read and write access to all databases and full access to the administrative queries, which makes sense because they're admin users. Then you got non-admin users. They are users that can only have the following three privileges: read, write, or all. And all means read plus write. So this is quite simple. I'm going to create a user, an admin user. I'm going to do login as an admin user. We're going to do create user Jorn with the password with all privileges. All privileges mean admin user. So he has privileges to everything. A non-admin user, on the other hand, it's very simple. It's the same principle, only just create a user and give it a password, but don't specify any privileges yet. We're going to grant them later on. So you do create user Jorn_read with a password. Then you do grant read on holiday France to the person you want to grant the read access to. And boom, Jorn read only has read access on holiday France. Can do the same thing with, like, let's say write, or if you want to make Jorn give read and write access, then it's simple to do a grant all on holiday_France to Jorn_RW. Let's say a person leaves the company, or you tested a plugin and it didn't work that well. You can always revoke or delete the user. So revoking a user is simply revoke all on holiday France, for example, from Jorn read. This means Jorn will not be able to read that database anymore, but the user still exists. So as we've seen in the previous chapter, you need to drop that user. As an admin, or from an audit perspective, you sometimes want to know who has what privileges and what applications are using your database. You can do that by doing show grants, for example, Jorn read. And then we'll show you where I have access to. You can do the same with users, like show users, and then you can see which users are created and then dig down into the users to see what access they have on which databases. So this was authorization and authentication. I strongly recommend you implement this as soon as possible. If you're testing on your local machine, that's no biggie, but please, if you install it somewhere in the cloud or in a data center or on any machine that has a public IP address, please do this first before continuing with the exercises or anything more. Thanks. Another cool feature in InfluxDB are retention policies. A retention policy, RP, is the part of InfluxDB data structure that describes for how long InfluxDB keeps the data. InfluxDB compares your local server's timestamp to the timestamps on your data and deletes data that are older than the RP's duration. A single database can have several RPs, and RPs are unique per database. Assuming that in the long run we're only interested in the average number of orders by phone and by website at 30-minute intervals, we could use retention policies and continuous queries, which I'll be explaining next, to automatically aggregate the 10 seconds resolution data to 30 minutes resolution data and automatically delete the raw 10-second resolution data that are older than 2 hours. Automatically delete the 30 minutes resolution data that are older than 52 weeks. Duration. The duration clause determines how long InfluxDB keeps the data. The duration is a duration literal, or inf for infinitive. The minimum duration for retention policy is 1 hour and the maximum duration is infinitive. Replication. The replication clause determines how many independent copies of each point are stored in a cluster. Keep in mind that a cluster is an enterprise feature. Where n is the number of data nodes, replication factors do not serve a purpose with single node instances. Shard duration. The shard duration clause determines the time range covered by a shard group. The duration is a duration literal, does not support an infinitive duration. This setting is optional. By default, the shard group duration is determined by the retention policies. In this example, you see create retention policy 1_day_only on a database, duration 1 day, replication 1. This means he's going to keep the data for 1 day. If you don't want the hassle to set custom retention policies, you can also alter the default retention policy. Let's say create retention policy 1 day only on a certain database, duration almost 24 hours, replication 1, and you end the query with the word default. This is going to set the default policy. You can also alter retention policies. Just type alter retention policy with the retention name, on which database, and you set the according values you want to alter. Here's an example on creating a retention policy and altering it. So first it was 2 days with a replication of 1, then we're going to alter it to 3 weeks with a shard duration of 30 minutes and its default. You can also delete or drop a retention policy by entering drop retention policy, the name, and on which database. This is going to delete the retention policy. A successful drop retention policy query returns an empty result. If you attempt to drop a retention policy that does not exist, InfluxDB does not return an error. Another super interesting feature in InfluxDB are continuous queries. Continuous queries, CQs, are InfluxQL queries that run automatically and periodically on real-time data and store query results in a specified measurement. CQs operate on real-time data. They use the local server timestamp to group by time interval and InfluxDB present time boundaries to determine when to execute and what time range to cover in the query. CQs execute at the same interval as the CQ query's group by time interval, and they run at the start of InfluxDB present time boundaries. If the group by time interval is 1 hour, the CQ executes at the start of every hour. When the continuous query executes, it runs a single query for the time range between now and now minus the group by time interval. If the group by time interval is 1 hour, let's say, and the current time is 17 hours, the query's time range is between 16 hours and 1659.99. So it's pretty accurate. We got basic syntax and advanced syntax. This is the basic syntax. The CQ query requires a function, an into clause, and a group by time. Notice that the CQ_query does not require a time range in a where clause. InfluxDB automatically generates a time range for the CQ_query when it executes the continuous query. Any user-specified time ranges in the CQ_query's where clause will be ignored by the system. We can use continuous queries to automatically downsample. Here is a simple example of how to do that. You can use a simple continuous query to automatically downsample data from a single field and write the result to another measurement in the same database. CQ_basic calculates the average hourly number of passengers from the bus_data measurement and stores the result in the average_passenger measurement in the transportation database. CQ_basic executes at 1 hour intervals, the same interval as the group by time interval. Every hour CQ_basic runs a single query that covers the time range between now and now minus the group by time interval. That is, the time range between now and 1 hour prior to now. You can also do continuous queries that automatically downsample data into another retention policy. Here you see CQ_basic_RP. It calculates the average hourly number of passengers from the bus data measurement and stores the result in the transportation database, the 3_weeks retention policy, and the average_passengers measurement. CQ_basic_RP executes at 1 hour intervals, the same interval as the group by time interval. Every hour, CQ_basic_RP runs a single query that covers the time range between now and now minus the group by time interval. That is, the time range between now and 1 hour prior to now. CQ_basic_RP uses continuous queries and retention policies to automatically downsample and keep those downsampled data for an alternative length of time. You can also have continuous queries with offset and time boundaries, as you see in the example here. The CQ_basic_offset calculates the average hourly number of passengers from the bus_data measurement and stores the result in the average_passenger measurement. CQ_basic_offset executes at 1 hour intervals, the same interval as the group by time interval. The 15-minute offset interval forces the continuous query to execute 15 minutes after the default execution time. CQ_basic_offset runs a single query that covers the time range between now and now minus the group by time interval. That is, the time range between now and 1 hour prior from now. The 15-minute offset interval shifts forward the generated preset time boundaries in the continuous queries where clause. Continuous queries advanced syntax. Continuous queries operate on real-time data with an advanced syntax. Continuous queries use a local service timestamp, the information in the resample clause, and InfluxDB present time boundaries to determine when to execute and what time range to cover in the query. Continuous queries execute at the same interval as the every interval in the resample clause, and they run at the start of InfluxDB preset time boundaries. If the every interval is 2 hours, InfluxDB executes the continuous query at the top of every other hour. When the continuous query executes, it runs a single query for the time range between now and now minus the for interval in the resample clause. If the for interval is 2 hours and the current time is, let's say, 17 hours, the query's time range is between 15 hours and 1659.99. Both the every interval and the for interval accept duration literals. The resample clause works with either or both of the every and for intervals configured. Continuous query default to the relevant basic syntax behavior if the every interval or for interval is not provided. Here is an example of a continuous query using the advanced syntax. CQ_advanced_every calculates the 1 hour average of passengers from the bus_data measurement and stores the result in the average_passenger measurement in the transportation database. CQ_advanced_every executes at 30-minute intervals the same as the every interval. Every 30 minutes, CQ_advanced_every runs a single query that covers the time range from the current time bucket, that is, the 1 hour time bucket, that intersects with now. Notice that CQ_advanced_every calculates the result of the 8 a.m. time interval twice. First, it runs at 8:30 and calculates the average for every available data point between 8 and 9. Second, it runs at 9 a.m. and calculates the average for every available data point between 8 a.m. and 9 a.m. Because of the way InfluxDB handles duplicate points, the second result simply overrides the first result. Using a for interval in the resample clause to specify the length of the continuous query's time range. CQ_advanced_for calculates the 30-minute average of passengers from bus_data measurement and stores the result in the average_passenger measurement in the transportation database. CQ_advanced_for executes at 30-minute intervals the same interval as the group by time interval. Every 30 minutes, CQ_advanced_for runs a single query that covers the time range between now and now minus the for interval. That is, the time range between now and the hour prior to now. Notice that the CQ_advanced_for will calculate the result for every time interval twice. The CQ calculates the average for the 7:30 time interval at 8 a.m. and at 8:30. And it calculates the average for the 8 a.m. time interval at 8:30 and 9. You can also use an every interval and for interval in the resample clause to specify the continuous query's execution interval and the length of the continuous query's time range. CQ_advanced_every_for calculates the 30-minute averages of passengers from the bus_data measurement and stores the result in the average_passenger measurement in the transportation database. CQ_advanced_every_for executes at 1 hour intervals, the same interval as every interval. Every hour, CQ_advanced_every_for runs a single query that covers the time range between now and now minus the for interval. That is the time range between now and 90 minutes prior to now. Notice that the CQ_advanced_every_for will calculate the result for every time interval twice. The CQ calculates the average for the 7:30 a.m. interval at 8 and 9 a.m. Results in the average_passenger measurement in the transportation database. Where possible, it writes the value to 1000 for time intervals with no result. CQ_advanced_for_fill executes at 1 hour intervals, the same interval as the group by time interval. Every hour, CQ_advanced_for_fill runs a single query that covers the time range between now and now minus the for interval. That is the time range between now and 2 hours prior to now. This fill will fill every empty value with the value 1000. So we're going to look how to integrate a chronograph with InfluxDB. Chronograph is the administrative user interface and visualization engine of the platform. It makes the monitoring and alerting for your infrastructure easy to set up and to maintain. So Chronograph is a complete dashboarding solution. It has example dashboards. It visualizes administrative tool for your Influx data deployments, and it provides user management and user authentication. It's a user interface for a capacitator. Alright, first we're going to start by adding some data points into InfluxDB. So we have some, I'm going to run the same command over and over again just to have some points I can show you. Then we're going to run the chronograph container with the option -- link to InfluxDB. This means Docker will open a network between the two containers, so chronograph is able to reach InfluxDB. So it started already, it's super fast. So we open our browser to port 8080. You can see I just opened it. You get a lot of feedback back. Put this here so you can see it. Then we're gonna check on if it's working actually. See, it says it's connected. So that's already working. We're gonna do, you can see the host list. If you have Telegraph installed somewhere, the host will pop up here with the metrics you're sending it. We can do a data explorer. We can do new query. As you can see, you see the data here. I was inserting the data to MyDB. CPU load short, give me all the values back. Give me everything from server 2 in US West. And boom, we have created our first dashboard. So this is super easy to do. It even auto-generates the query, as you can see. You probably wonder, why didn't you show us that in the beginning of the course, so you don't need to learn the InfluxQL, but it's very important that you know how to do that yourself as well. So there are a lot of graphs you can draw here. I suggest you play around with it so you can create your own dashboard, add a graph, and then visualize your whole stack or whatever you want to graph. Like I'm gonna do it here. I'm going to show you MyDB, CPU load short, host server 2 in the region US West. Give me all the values. See, and we have created our first dashboard. See how super easy this is? If you see in comparison with Grafana and other tools, sometimes they can be a pain in the ass, but this is really super simple. I hope you enjoyed this lecture. Alright, and just like in the previous chapter, I will be adding some random data to InfluxDB, so we have some data points which are recent to visualize. Now we're going to start the Docker container. We're going to do a Docker run -- name Grafana InfluxDB -port 8080 to 3000, which is the Grafana port in the Docker container. So we're going to expose it to this host, localhost to 8080. We're going to link it with the InfluxDB container, and we're going to use the latest Grafana container. So it's executing. If it's the first time you run this, you will be pulling the image. If the output doesn't correlate with what you're seeing right now, it's because he has to first pull down the image, extract it, and then you will see the same output. But the beginning can be different if you don't have the container cached in your local system. So we're going to open a browser right now. We're going to go to localhost 8080. You can see he already got a request. This is the Grafana login page. The default username is admin. The default password is also admin. Better change that password if it's installed on the cloud. Then we're going to add a data source. We're going to name it InfluxDB Udemy course. It's type InfluxDB. It's not on localhost, it's on InfluxDB port, because it resolves within the Docker container. It resolves to this URL. I'm gonna use the database MyDB. Gonna add it. Data source is working, so we didn't have to push save and test. Okay. Now we go to data sources, list view. Got InfluxDB right here, so everything is set up right now. Now we're going to dashboard. I'm going to create a new dashboard. I'm going to draw a graph. I'm going to go here, press edit, and see, this is super simple again. It's so useful. They put such an effort into this that this works so great. It's really cool. So we're going to do a select measurement, CPU short, where host is server 2. And you immediately see the data points which we added like a couple of seconds ago. This is super cool, right? Now I'm going to save this dashboard, new dashboard copy. I'm going to give it some more Udemy dashboard, Udemy awesome dashboard. Boom, and we got it here right now. See, those are the measurements we added. I'm going to select the range. Last 5 minutes, go back. Where did it go? Last hour. Oh, we were zoomed in, sorry. See, and here you can see the data we added. This is the previous lecture, and this was from this lecture. So that's how simple it is to draw dashboards in Grafana. Hope you enjoyed it. See you next time. InfluxDB monitoring. In this section, I will show you how to build a free, scalable, and integrated open source system for processing time series data. In this case, a monitoring solution. For this, we're going to use the tick stack. The tick stack is composed out of Telegraph, InfluxDB, Chronograph, and Capacitator. You can, however, use each of these components separately, but if you use them together, you have a scalable, integrated open source system for processing time series data. In this tutorial, you will set up and use this platform as an open source monitoring system. You'll generate a CPU spike and receive an email alert when the usage gets too high. You can of course extend these alerts to whatever metric you have. For this lab, you'll be needing one Ubuntu server. We're going to use one on DigitalOcean, but you can use whatever you want. I'm going to put a referral code in the course notes so you can get one for free if you don't already have a DigitalOcean account. We're going to use an SMTP server, or in this case SendMail. In this lab, we're going to follow the following steps. We're going to be adding the tick stack repository, installing InfluxDB, and configuring authentication, which is very important because machines on DigitalOcean are publicly facing. Install and configure Telegraph, install Capacitator, install and configure Chronograph, and then we're going to configure some alerts. So alright, let's start with step 1. We're going to add the tick stack repository. So the tick stack components aren't available through the standard packet manager by default, so we're going to add it. All tick stack components use this repository, and we'll set up a repository configuration file to make installation seamless and easier for like upgrades or whatever you want to do next. So first up, we're going to get the key of the repository. Then we're going to load the release file. Then we're going to put everything needed into the repository file. Okay. So let's check if everything is added correctly. You can see repo, Xenile, and stable. Perfect. Now we're going to update the repository to make sure everything is loaded. Okay, it's loading. That looks good. Okay, excellent. So as you can see, he got all available packages through the repo. Now we're going to go to step 2, and that's installing and configuring InfluxDB. So I'm going to install it. Great. And already start InfluxDB just to see what it does. Do a status. You can see it's running. Okay. InfluxDB is an open source distributed time series database. Also looks good. Started 6 seconds ago. Great. And we can log in. So at this point, there's no authentication on InfluxDB, so I really encourage you to do this step as this machine is publicly accessible. If you're using DigitalOcean or another cloud provider, which doesn't include your server being in a private subnet, you really have to do this. So we're gonna do create user InfluxDB lab with password Udemy lab 123. Of course, you can use whatever username or password you want. All privileges. Great. Show users. Aha. Here we have the user. Perfect. Now we can exit. And then we're gonna enable the authentication. So we're gonna do vi etc influxdb influxdb.conf, and then we're gonna look for auth enabled. So this is false. I'm gonna put this on true. Quit it, and then we're gonna do sudo systemctl restart InfluxDB. Oh, I misspelled restart, sorry. Here we go. Right. So now we installed InfluxDB, and next we're gonna install Telegraph. So it's the same principle. Telegraph is an open source agent that collects the metrics and data on a system it's running on. So this should be installed distributed if you have, or you want to monitoring multiple machines at once. So, but in this lab, we're going to put it on the same machine just to keep the cost down if you're paying for instances, or to keep it easier to debug. Then we're going to install Telegraph. So it should be started ctl status Telegraph. Should be installed automatically and started as well. See, it's running great. Because we enabled InfluxDB authentication, we need to point Telegraph into the right direction and give it the correct credentials. So I'm gonna vi, gonna look for username. Okay, I'm gonna unquote this. We're gonna make it InfluxDB lab. Was InfluxDB Influx. Okay. Was Udemy lab 123. Great. I'm gonna do system ctl restart Telegraph. So that, great. I'm gonna do a status again to see if it started correctly. Alright, that looks great. So you can see it's loaded and it's running, so that's good. Now we're gonna do get the file. Alright, that looks good. Now we're gonna see if he created a database, InfluxDB client. Alright, I'm gonna do show databases. See, and he says you're not properly authenticated, so we need to do influx dash username. That one was InfluxDB lab. Password password is Udemy Lab 123. All right, now I'm going to do show databases. And we see we got one extra database called Telegraph, which is great. I'm going to do use Telegraph to see what's in there actually. Then I'm going to see what metrics he's reporting on. Measurements. So he's reporting on CPU, disk I/O, kernel, memory, processors, swap, and system. So he's already working actually now. So Telegraph has like 60 or more plugins, so you can report metrics to InfluxDB, let's say for Apache, Cassandra, Docker, Elasticsearch, IP tables, MySQL, Graylog, PostgreSQL, Redis, SNMP, and so much more. These are the most commonly used, at least the ones I use. If you want to see, for example, Telegraph usage of let's say Redis, you can see how to use this Telegraph plugin for Redis. So it's quite simple to hook everything of your stack into one monitoring solution, which is free. So if you're using a small instance on DigitalOcean for, let's say, or even AWS, it wouldn't cost you much. It is self-hosted, but nevertheless, it's free as well. So now we got metrics coming into InfluxDB. The next step is to install Capacitator. So Capacitator is a data processing engine. It lets you plug in your own custom logic to process alerts with dynamic thresholds, match metrics for patterns, or identify statistical anomalies. We, in this lab, will use Capacitator to read data from InfluxDB and generate alerts, and send those alerts to specified email addresses. So first up, I'm going to install Capacitator. Okay, I'm going to edit the config file. I'm going to look for username and password. Okay, Udemy, no, that was InfluxDB Lab. And this one is Udemy Lab 123. Alright, great. Now we're gonna have to restart it. So we're gonna see if systemctl status Capacitator. So it's loaded, it's enabled, but it's inactive, so it's not running. So we're gonna have to start it. So systemctl start Capacitator. See if it's running again, and it's running great. They even have put some nice ASCII art into it, like the Capacitator logo. Capacitator list tasks. You see there are no tasks running. Next up, we're gonna install Chronograph. Chronograph is a graphing and visualization application that provides tools to visualize monitoring data and create alerts and automation rules. It includes some support for templates as a library of intelligent pre-configured dashboards for commonly used data sets. We're going to configure it to connect to the other components we installed. So I'm going to install Chronograph. Okay. I'm going to see if it's running. Chronograph. Alright, it's running, and I'm going to check it out in a browser. Alright, now Telegraph is installed. We can try to connect to InfluxDB. Use this password to add source. And as you can see, it's connected. Let's see if the host reports. This looks great. And here you can see the metrics we already have about the system, which is pretty cool, right? Now it's connected to InfluxDB. We're also gonna try to connect it to the capacitor. So I'm just gonna go here, configuration, add config. All right, so it's connected. Here you can see where you want to alert to. You can choose HipChat, Opsgenie, PagerDuty, pushover. You got so many. VictorOps, talk. You got so much here. The simplest method of communication is SMTP. So it's basically just sending an email. What you can do is install SendMail or use your own like Gmail or whatever you want to use. In this case, I'm going to use the Gmail's SMTP server. That's smtp.gmail.com. It's port 587. It's not the default port. We're going to send the emails from my own email address. So just to make sure we're not in the spam. Okay. Then we're going to add the password. I'm going to update SMTP config. So right now, if you send an alert through Capacitator, it will be able to reach your email, which you configured here. Right now, we're going to configure an alert. We go to alerting, then create, build rule, high CPU. Gonna work on a threshold. We're going to look into our database. So Telegraph CPU, and then we're going to look here for usage user. As you can see, I've been playing around with it for quite some time before I started the lab. So right now, let's say we want to get alerted if the CPU is higher than 15%. So when you enter 15, for example, he will show you the thresholds here. So on all these events, he will be alerting. Then we're going to say send this alert to SMTP. And then we can specify a body text that goes here, or you can just add this one. So I'm going to do the ID, the name, the task name, the group, the tag, the level, index field value, and the time. So we're sure we got enough information when the alert gets in. So this is an optional alert parameter because we entered the alert email address in the previous configuration. You can enter or add more from your coworkers or your PagerDuty email address or whatever you want to fill in here. Now we're going to save the rule. That's it. So right now the monitoring is live. So now I'm back logged into my InfluxDB server, and we're going to generate some load. So we're going to do that by yes. We're going to redirect that output to def null. This will generate some CPU, normally around 20% depending on the machine you're having. Alright, great, this is running now, so we're going to head back to our browser. See, we got a high CPU. Gonna go to our host list, check it out. See, it's almost there. So it should be alerting almost. It can take some time though. So we're gonna look in the history here, and yep, it's alerting. These previous ones were from previous experiments, but as you can see, the level is red right now. And if we're gonna stop the CPU load, I'm gonna Control C that, so it stopped. We'll see it's gonna go green quite fast. So I'm gonna refresh that. And it's green again. So let's check our email to see if I got an email message. As you can see, this email isn't very sexy, so just because we didn't add any formatting or whatever to it, you can choose that if you're like that. For me, this is sufficient to show you how to set up alerts through Capacitator and InfluxDB. I hope you enjoyed the lab. Bye. Chronograph authentication. The prerequisites of this lab are running TickStack and a GitHub account. If you don't have a running TickStack available, I encourage you to follow the previous lab. In this lab, we'll set up a chronograph with a OAuth 2.0 authentication. Chronograph supports out-of-the-box GitHub, Google, Heroku, and Auth0. We'll be setting up a GWT signature, which is a random string. It's needed for all OAuth 2 providers. It's to verify user authorization and allow users to stay logged in. The JWT signature is provided as the token secret environment variable. So if you want to force logout to users, you have to change this token on the restart of Chronograph. In this lab, I will also show you how to use systemd and how to check what config file is used and what environment variables he's reading. Alright, let's get started with the lab. So first up, we need to go to github.com. If you don't have an account, I encourage you to create one. Once you're logged in, you go to Settings. Then you go to Developer Settings. As you can see, I don't have any OAuth applications running at the moment, so I'll register a new one. We'll call it InfluxDB Udemy Lab. You have to specify a homepage URL and you have to specify an authorization callback URL. As you can see, I installed everything default and this is the IP of my server. We're going to register this application. Here you got the client ID and the client secret. We're going to copy paste this because we need this later on. Alright, now we need to log into our server. So when you're logged into your server, you're going to do systemctl status chronograph. You can see here, this is a configuration file that systemd uses to start chronograph. I'm going to VI this. As you can see here, you got the environment variable file that chronograph is using when it starts. So we're going to copy that. I'm going to quit. I'm going to edit the file. As you can see, this is empty. So we need to specify a couple of parameters in order to let this work. We need the auth duration. This is the time that the JWT token is valid. Then we got a token secret. And then we got the GitHub client ID and the GitHub client secret. There we go. Now let's first go to Chronograph. So right now we haven't restarted Chronograph, and as you can see here, we're still logged in. So I'm going to switch back to the server and restart Chronograph. I'm going to do a systemctl status Chronograph, and it's running and everything looks fine. Now we're going to switch back to the browser to see if we're logged out, and as you can see, we're logged out. So I'm going to refresh this page. I'm going to log in with GitHub, going to authorize myself, and bam, we're logged in. So this is how you enable authorization on Chronograph. This is really encouraged when you have a public facing machine so you don't expose your data.